I thought you should be happy. You're finished. Not happy?
I have to finish until Thursday.
Yeah, and then you're free. Freedom.
Well, I'm fed until Thursday.
Why? You want more time?
Yeah.
How much time?
I don't know.
No, seriously, guys. Is Thursday too soon? Do you need more time or not?
I'm polishing.
Yeah, so how much time do you think you need?
Maybe we can do that.
Well, make it Monday. Like, Monday after the Thursday. Ken, what do you think? Monday after the Thursday.
Next Monday. No, next Monday.
Yeah, like Monday plus 1 week. Would that be okay? Yeah? Yeah? Okay. Monday plus 1 week. Fine. Okay. Right. Let's continue. So we'll do a lecture and then we can do a tutorial. We might have to split this lecture up, I don't know, big enough. Hooke's law. Oh, and thank you. Okay, you got that? Where's Chow? I saw him downstairs.
Still downstairs.
What's he doing? Is he smoking? Like what?
No.
Okay. Hooke's law, you got that? Yeah. So, right. Got us thinking about this. You notice with something like this, what happens as you pull more on this spring? So as you pull it out more, you should feel or you should need more force. Yeah? Yeah, you should need more force. So this actually, it's actually quite simple, but it's called Hooke's law in physics. The idea is as you stretch. Oh, thank you, Andy. Go on, Joe. What took you so long? What were you doing downstairs?
Downstairs?
Yeah.
I got a phone call.
Okay. Right. So, as you pull on the spring more, there's more force. Hooke's law actually tells us the relationship. Hooke's law says that the force that you need to extend a spring at distance x is proportional to the distance. That is, F is equal to minus kx. So what Hooke said is, if you pull it twice as much, then you need twice as much force. Or if you extend it 3 times, then you need 3 times the force. The k is a constant which is different for each material. And the reason for the minus is the idea that if you pull it, then the force you have to cancel is moving the other direction. So if I pull it this way, then there's a force trying to pull it back the other way. Okay. The k is a constant. What's the unit for k? What's the unit for k? Yeah, newtons per meter. It's called the stiffness constant. X is small usually, and the k unit we said is newtons per meter. I think the other thing here to note is that because the x is small, sometimes I might write it as delta x to mean small x. Okay. Now the F is called a restoring force. If you have something stretchy like this here, if I stretch it out, it wants to snap back. So the force is called a restoring force. It tries to restore it back to its original length. Okay, and the X is called an extension, and the K is called the stiffness constant. So if the K is really big, then does that mean it's easy or difficult to stretch it? What do you think?
Difficult.
It's difficult, yeah. And if the K is really small, it's easy then. Okay, so what about a material like wood? Be big or small?
Big.
It'd be big, yeah, because you can't really stretch it. You actually can a little bit. You know, like if you apply a force, it actually does stretch a little bit. You can see this, of course, in some pieces of wood that kind of have a little bit of flexibility to it. Okay. So for the exam, when they ask you for Hooke's law, they can either give it to you can either give it in words or as a formula. If you choose to give it as a formula, you have to say what each of these letters represent. Or if you give it in words, you can just write it as a sentence. So you choose which way you want to write it down. Okay? I think I know which one you'll pick. I think most of you will pick the formula, and I think Chow will write the words. Yeah. Got that? Yeah? Got that? Yeah? Okay, so some more definitions. So when we say the natural length, L, it can be of many different materials. It's the length at which the material tends to return to. So in other words, the natural length is the length it would want to be if there was no force on it. It's the length before there's any force applied. That is, it's the length it wants to be at. This is the natural length. Is this a new word, by the way, or is this a word you've heard before? Natural length. You've heard of it before? Yeah? And not that difficult of an idea. Continue? Yeah. So, more definitions, I'm afraid. The extension. What do you think I mean when I say extension? What does the word extend mean?
Expand.
Like expand, or if we're talking about strings and springs, what could it mean? Like a stretch, isn't it? It's actually the distance you stretch it. Okay, so the extension of a material is the length at which the material is extended beyond its natural length. That is the x in the formula. You got that? Yeah? Now, what does this graph represent? So, what you've done here is you've taken a spring and you've extended it by increasing amounts, and then you measure the restoring force. So just to give you a picture of what this might look like, it could be something like, let's see, you have your spring, and that's its natural length, okay? So that's the length it wants to be at normally. And then you attach at the end of it what's it called? I think it's called a spring balance. No, is it called a spring balance? Not sure. Anyways, you pull at the spring, and as you pull at it, you can measure the force. It's like a little scale on it. So you pull it out a distance maybe of 0.1, then you pull it out a distance of 0.2 meters, and then you measure the force. So what do you think will happen as you increase the x here? What will happen to the force? It'll increase. If you don't extend it, what should the force be? 0, okay? So in this graph here, you have your extension and you have your force. Now, what is the slope of this graph? Let's calculate. So if you were to get the slope, you know, like let's say it's the height rise, the delta y over the delta x, the rise over the run. So it would basically be a force on the top and an extension on the bottom. Okay. If you think about your formula, f equals minus kx, what does f over x represent? F over x here, over x, yeah, is k. Yeah. Now we don't really need the minus because we know this force is actually to the left, so it really is negative. So actually this is the k. In other words, the slope of this graph represents the k. So if it's a stiff material, then should the line be higher up or lower down? What do you think? If it's it should be higher up, a bigger slope. And if it's a flexible material, it'll be lower down. Okay. So this is a force against extension graph, and the slope of the graph represents the k. So this is an experiment you could do to calculate the k. More interesting now is what does the area represent? So let's have a look at that now. So if I scroll down a little bit and we have a look at the graph, we want to know what the area represents. So let's say the area from here to here. Well, let's calculate it. This is x and this is in f. So the units here are meters and the units here are newtons. So what would be the units of the area? And m. What's newton meters? What unit is that? Joules. And what does joules represent? Energy. Energy or work, yeah. So what do you think that means for the spring? What could that area represent? Good potential energy, yeah. Or if we think about this story here, what does it represent? Yeah, what exactly? Yeah, so in other words, the area represents how much work was done to stretch the spring out to its length that you have. Okay, so here the extension is 0, here the extension is 0.4. So this area here represents how much work was done to take it from 0 extension to 0.4 extension. You understand? Yeah. If you calculate part of the area, like from 0.3 to 0.4, then that represents the work done to extend it from 0.3 to 0.4. Okay. So the answer is my box is cut off. Okay. Anyways, we have the result here. The slope represents the k, and the area represents the work done, and this is when you have a graph of extension and force, and the graph is like this. Okay, so my box is cut off, so if you can just write this down. Well, did you draw this? You should draw this, and then you can write this down. And are they your chocolate Rice Krispies?
Yes, correct.
Kim, they're your chocolate Rice Krispies. Could I have one, please? I'm so terribly hungry. I need to have something. Thank you. I just want to take one. I won't eat them all. Is this your breakfast? Okay. Snack? I don't know how students can skip their breakfast. I had breakfast and I'm getting hungry. Who are the breakfast skippers in this class? Oh, tut. You too? Breakfast skipper? Good, good. You're a breakfast skipper? Chow? You eat breakfast or not?
Yeah.
Oh, good. Oh, good, okay. Do you not find yourself starving?
Yeah. Get used to it.
Not terrible. It's tragic. Okay, did you draw this?
Mm-hmm.
Okay, and did you write this down? Yeah. Okay. Continue? Yeah. Okay. So, that's all. Sure, let me just go back to this. Okay? Now, oh dear. Okay. In real life, the graph doesn't quite look like this, because you understand that if you pull it enough, what will happen? Yeah, what will happen?
It becomes straight.
Yeah. Oh, I mean, what would happen to the material?
Like it wouldn't keep stretching.
Yeah. Like, it's only stretchy up to a certain point. In fact, you could pull it so much that it breaks, okay? But also, for some materials, if you stretch it too much, then it loses its ability to return to its original shape. I think you could see this maybe, you see this actually with clothes, you know, your fabric of your clothes. If you stretch it too much, it won't snap back to its original shape, okay? This happens when you lend clothes to people who are bigger than you, and you get it back and it no longer returns to its original shape, okay? So, we understand that this graph isn't realistic. In fact, the graph is actually a little bit more like this. You know what, I'll draw it here. Extension and force. So we understand, okay, we pull it, we get force, we pull it, we get force, we pull it, we get force, and then we reach a point where we pull it a little bit more, but we don't get as much force. It's like it becomes less stretchy. It won't snap back to its original shape. So then the force starts to level off and reach a maximum. And then I guess if we keep continuing to pull it, we might actually break it, and then we'll get no force. But they don't talk about that in the exam, they just care about this much. Okay? So, this graph has three important stages. Here to here, it behaves one way, and then here to here, it behaves a different way. And this point represents when it changes. So we call this point here the elastic limit. Okay, I should say it's common enough in the exam that they ask you to draw this graph and they want the parts labelled. So this part here has a name, and this part here has a name. So you won't be shocked to know that this part of the graph is called the elastic region. That's not too shocking, I hope. What do you think this part is called? I love it. You see, I ask it every year hoping somebody will say that, because it seems like it should be, shouldn't it? You have elastic, so this is inelastic. In fact, not. That's not the opposite here. So what's the opposite of elastic? It's not inelastic. You think it's inelastic, it's not inelastic. You have elastic and what's the opposite? Good. Not this, but you're thinking correctly. It's some other word. It's not quite stiff, because stiff means that you can't move it at all. Whereas here you can still actually stretch it. It's just it doesn't have its same snappiness.
Hard.
Again, hard, it doesn't really mean that you can stretch it. You know what I mean? Like, we need a word that means it's still a bit stretchy, but it doesn't snap back to its shape. So think of a word. It means you can stretch it, but it doesn't snap back to shape. Any other word? Huh? Yeah, you're getting closer. Flexible is a little bit too stretchy. So we need something less stretchier than flexible. Any ideas? You've given me some good ones, Siba. You're nearly there. You're getting close to it. See, if you had breakfast, I think you would think of it. Anybody? Nobody else wants to try? No? You let Siba do all the work? No? Any ideas? Okay, I'll tell you. It's a word you know. This is called the plastic region. Plastic means you can change the shape, but you don't have a snappy force bringing it back together. Okay, yeah. Obviously plastic has another meaning as well, like when you talk about plastic materials, you know. But here it means, it's like describing its stiffiness. I'm not sure what the word is. It's flexibility, how flexible it is. It's plastic. Okay. Continue. So, in fact, Hooke's law is only true here. This is where Hooke's law would work. It doesn't work in the plastic region. Right, so some terms. So, elastic, we know what that means. It means the material obeys Hooke's law. Plastic means it doesn't follow Hooke's law. Elastic limit, what would we say the elastic limit is? yeah, I like it, yeah. When it stops obeying Hooke's law, yeah. The point where it's no longer elastic and becomes plastic. Although in the exam, Matt, I would take your explanation as well, that's fine. Okie dokie. You got that? Yeah? Yeah? Ciao? Okay. Okay. A mass M is hung to an elastic material which hangs from the ceiling, or a mass M sits on top of a spring. In both cases, the situation is the same. The mass at the end will obey Hooke's law. So, picture you have something from the ceiling, like a spring or a rubber band, and you hang a weight at the end of it. Okay? If you pull the weight down and let go, what happens? Well, obviously it will shoot up. And then what will happen? It will fall back down. In fact, you'll get a simple harmonic motion. The same is true if you had like a spring, you had a mass on the top, and you push it down and let go, what will happen? You get the simple harmonic motion. Or again, if it's against the wall and you pull it out and let go, you get the simple harmonic motion. So, the simple harmonic motion goes together with Hooke's law. When you have Hooke's law, you also tend to have simple harmonic motion. Okay. Now, let's look at the first case, but the formula will actually work for the both. So, okay. There's a big proof coming up. It's not on the exam, but I think it's good for your physics education if you see the proof. Okay. So if you can write this down, and we'll take our time. Okay, so here's our ceiling, and here's our length L rubber band. Then what I do is I very gently hang a mass on it. Just carefully put a mass on it. So what will happen if I do that? Well, it will stretch a little bit, won't it? So now it's down to here. Now, if I'm careful, it shouldn't be moving. You know what I mean? Like, if here's the spring, and I just hang a weight onto it, like, carefully, it should just be pulled down a bit. Okay? Let me calculate how much it falls down. Alright? So if you look at this picture, there are two forces acting. What are the two forces on the mass here? Weight, yeah, which is mg. And here? The tension. And this tension is a Hooke's force, because it's a stretchy spring. So Hooke said that the tension is equal to minus kx. Now I'm not putting the minus in because I know it's up. I know the direction. Okay. You actually know that these two forces should be equal. Yeah? Because it's balanced, it's not moving. So what does x equal? mg over k. Alright, so let me draw this picture again. Here it is here. And what's the length? The length is L plus mg over k. That's what I'm saying. Okay. Now, the interesting part. You come along and pull this down and let go. Now what will happen if you do that? It will start to move up and down, up and down. Okay? So before I continue, I'll just let you write this much down. Okay, you got that? Matt? No, okay. Okie dokie. Yeah? Continue? Okay. So, let me just draw our picture a little bit clearer here now. This is L plus, what did I say? Mg over K. Alright. So, this line here, this is like the rest position, the equilibrium position. And then what you do, you come along and you pull it down this much. And then it will start to move up and down, up and down. So as it's moving between here. Oh well, I'll just draw it a little bit more accurately. Up and down, up and down. So as it's moving between here and it would be here. So actually this is like A and this is minus A, the amplitudes. So let's imagine it's here, it's on its way up, and we'll call this distance here x. So the x is getting bigger and smaller, isn't it? What's the value of x at the beginning of the motion? It's a. And at the end of the motion, or at the other half of the motion, it goes up to minus a. So this x goes a, 0, minus a, 0, a. Up and down like that. Okay, let's calculate the force. So how many forces are on this here? 2 forces. Okay, so the total force is the force up minus the force down. What is the force up? Tension. And the force down? Mg. Okay, how do we get the formula for tension here? What do we use? The Hooke's law. Okay, so that's Kx minus mg. Okay, right. So let me just continue over here. Now I put a space here because we need to work out what the x is. You might think the x is just simply x, but that's not quite it. What do we say the x is in Hooke's law? Nearly. Remember we said in Hooke's law the x is the extension beyond the natural length. Okay, so let's calculate that. The length of the string is currently L plus mg over K plus x, because it's pulled down a little bit from here. Remember, L plus mg over K is this length here, and we have a little extra x. Okay, what's the natural length, did we say? Well, we said that's L. So therefore, what is the extension? If you compare these two, what is it? It's mg over K plus x. That's how much it's been extended beyond its natural length. So here, I don't put x, I plus mg over K plus x. Now, if I multiply that out, what do I get? Mg over K times K, that's going to be mg, plus kx minus mg. Well, they cancel. So you end up getting this formula. I think I forgot something somewhere. No, that's it. F equals kx. That's not actually too shocking. What does F equal according to Newton? ma. And so what does A equal? K over mx. Now, there is an issue with plus or minus here because it depends where it is. You know, if it's in my picture, I have my mass underneath. In my picture, I said down is positive and up is negative, right? But usually it's the other way around. So if I just change that for a moment, the acceleration is up, minus k over mx. Now if you think back to your formulas on simple harmonic motion, do you remember what the formula for acceleration was? A equals something by something. You might have to look back if you don't remember it. The formula for acceleration in simple harmonic motion.
Minus omega squared times s.
Yeah, or in this case we'll call it x. So if you were to compare these two formulas, what would you say the omega equals? Nearly. No, you were closer the first time. It's just you forgot about the root. Yeah, root k over m. Now, in the simple harmonic motion formulas, what did I say the time was equal to? It's 2 pi over, not f, try again. No. You can't, t is not 2 pi over t. T is 2 pi over omega. So that means t will be 2 pi root m over k. So this is our formula for the spring. If we have a mass m at the end of a spring k, the time is given by this formula. Now this looks like another formula you've seen before in physics. What does it kind of remind you of? Yeah, there's another formula that looks a bit like this, where you have to calculate the periodic time. Yeah, the pendulum. Do you remember what the formula is?
L over G.
2 pi root L over G. Whereas this one is 2 pi root M over K. You see this a lot in physics. When you have something that's in simple harmonic motion, often the formula for the time is 2 pi root something over something. Okay. Yeah. I'll let you write this down and then we'll continue. Look, just be thankful that you don't have to prove it in the exam, okay? You just need to know this formula.
But the projected ball is in the middle of rest and A or.
No, it's in motion. I'm trying to convey that it's the x is a variable in motion, you know.
Just read the formula.
I would like you to write it all, Chow, I'm sorry. I think it'll be good for your education. Sorry, just checking something here. There's only one more after this, for this chapter. What's really nice about this formula is it doesn't matter if you hang it from a ceiling, if you have it on the table, if you have it pulled against the wall. It's what's really nice is that it works in all these sort of oscillating situations with a spring or a rubber band or something like that. So it's an extremely useful formula, extremely useful. What is interesting about this formula, a bit like with the pendulum, if you pull it down more, do you affect the time? What do you think? No, because in this formula there is no mention of the amplitude. In fact, if you wanted to make the time bigger, what would you need to do? If you have a look at the formula, what would you need to change to make the time bigger? What would you have to alter? What would you have to change? No, don't be shy. You know this. Look at the formula. I want to make the t bigger. So what could I do?
Heavier.
Say again?
Heavier.
Yeah. Make the mass bigger. Make it heavier. Yeah. Or, what could I do to the spring? The length isn't in this, you see.
If you want to increase the time.
Increase the time.
Less.
Less K. And what does less K mean? What does the spring look like if the K is smaller?
Sure.
Not necessarily shorter. Sorry, I shouldn't say look, sorry. I should say, how would you describe a spring with a smaller K? Remember, oh yeah, I suppose, but use more like,
Flexible.
yeah, okay. Stretchier, boingier, springier. I think that's interesting, that it doesn't matter how much you pull it down, it's going to not affect it. It's a bit like with the pendulum, you know, it doesn't matter how far you pull it out, it's the same time. Yeah?
What's this? BUT?
Sorry, but, yeah, sorry. Yeah, I printed that out a long time ago. Okay. You got that? No, yeah, okay. You have this already, Kim? Mm-hmm. And Siva, you have it? Yeah.
Why d minus k over x minus k over x plus x?
What part is unclear?
The blue part. A equals minus k.
This part came from that part.
The next one.
Oh, this one?
Yeah. Why
It's only because the plus and minus is unclear because it depends where it is. You know, in my picture here, and it also depends on what you say is up and what you say is down. So normally when we look at formulas, we assume that it begins in the positive and it moves to the negative. Do you remember the simple harmonic motion? I said we assume it starts at the positive and decreases to the negative. So if I assume the same thing here as a starting point, it means I should really choose the minus, because I should really imagine it starts in the positive. The problem is my picture. When I drew my picture, I had it starting in the positive, but the positive was in the down. You know, so I kind of screwed up my signs. So I just fixed it later. Okay, you got this? Chow?
Mm-hmm.
Matt?
the last
No problem. Okie dokie? Yeah? Okay. Come on. I know, don't be stuck. Right, so we get this formula. T equals 2 pi root m over k. Notice that this formula doesn't contain a or l. Right, so I'm thinking. We also have to do a tutorial, right? You have questions you want to see done? Yeah, like how many questions do we think we need to do?
Yeah, I tried it today, but I cannot solve one.
You tried yesterday and you could not solve number 1.
Like any.
Any of them? That's worse.
Yeah, me too.
Where's my bag? What was yesterday's? Oh, the latent heat.
We call it top of the previous sentence.
Thermodynamics.
Genetic model of gas.
All right. Yeah.
Can you do that?
Yeah.
And me too.
Go ahead. So what page are we starting on? Japers, you're all going to the bathroom. All right. Don't be long. We'll start the tutorial when you come back. Okay? We will wait a minute. Okay? Everybody had too much teeth this morning, I think.